Thanks for the introduction, Mike. My name is Zhang. I'm a fourth-year PhD student from Carnegie Mellon University. Today, I'm really excited to be here presenting our work on Vibrosight, long-range vibrometry for smart environment sensing. This work was done with my colleague Gierad Laput and my advisor Chris Harrison. As we just heard from Gierad about in his talk that people have envisioned smart environment for decades, where our environment can not only passively take commands from us, but also understand the context and proactively adapt to it. This vision relies on a robust sensing method to detect human activities, such as chopping vegetables, writing on whiteboards, and doing exercises. As a result, much effort has been spent on activity sensing in previous work. For example, the most common approach uses camera with computer vision technologies. There are also acoustic approaches which leverages the sound resulted from the activity. A less common approach uses radio frequency and capacitive sensing. And finally, we can also attach sensor tags to objects for usage detection. These sensor tags can also be used to detect vibration, which is the byproduct of many user activities. In Vibrosight, we also detect vibrations, but uniquely at a long distance. From this previous work, we found several ideal sensing properties for activity sensing, which Vibrosight tries to achieve. First, we want to perform sensing from a single sensing point where the sensor can be easily set up and placed out of a user's sight, for example, higher up on the ceiling. We also want to achieve simultaneous activity detection, which was proved challenging in previous work. And finally, we want our sensor to be privacy-preserving, low cost, and high accuracy. Now let me talk about our sensing principle. We were inspired by the optical vibrometry invented by Leon Theremin in 1950s. This technique reconstructs vibration from afar using infrared light, and later used by the KGB in their eavesdropping devices. In this project, we did a modern twist on an old technology and for a very different application domain. Here is an illustration of how optical vibrometry works. We first have an emitter which bounces light off of a distant and reflective surface, in this example, a window. Vibrations of surface caused by the speech, or in our application, appliances running, alters the light path. We can place a receiver on the return light path to capture the light intensity. This signal can be used to reconstruct the vibration. Relying on existing reflective surfaces require calibrations between the emitter and the receiver. When we move the emitter or when we want to measure different objects, the receiver needs to be repositioned. Ideally, we want to put them in one small package and works with any angle and distances. There are two unique ingredients that allow Vibrosight to achieve this. First is the use of retroreflective tag, as we see here. They are cheap, durable, and can be placed on a wide range of surfaces. The second ingredient is the steerable mirror controlled by two stepper motors. And here you can see the vibration signal detected by our sensor shown on the laptop. And the tag is attached here. As you can see, there's a sensing laser dot on it. Before building our systems, we first want to verify the sensing principle. I'm going to quickly go through the experiments that we did. We first did a test on reflector material. We tested different materials, including a mirror, a glass, reflective spray, corner reflector, and retroreflective tapes. And we configured an actuator to output a sweep frequency and measure the reflected light with a photodiode sampled at 5 kHz. Here we can see the FFT spectrums. We found that the retroreflective tape works as good as the mirror and the glass. We then did a test on the laser wavelengths. So the three tested colors, green, red, and the infrared, worked equally well. So we decided to use the red laser for the ease of debugging. But ideally, we want to use infrared in real-world usage because they are invisible and thus is unobtrusive in the environment. Since Vibrosight uses optical sensing, it might be affected by the environmental lighting. To investigate this, we conducted a test with 4 lighting conditions: dark, daylight, incandescent light, and fluorescent light. We found incandescent light induces 120 Hz noise, and the fluorescent light induces more of a wideband noise. For this reason, we decided to include filters on our analog front end when we decided the PCB. We also wanted to know how angle and the distance affect the signal. So we fixed the actuator to output the frequency to 1 kHz and used our sensor to measure the vibration signal amplitude. Here is the result when we vary the laser angle. As we can see here, there's a significant drop between 0 degree, which is when the laser is being perpendicular to the tag, and 5 degree. But still, we can sense reliably up to 45 degrees. When we vary the distance, these results show that we can pick up the vibration up to 16 meters. We also did a test combining the two factors to investigate if there are any interaction effects, and we found that it's just a linear combination of the two. Now let's show a demo. I would like to invite my assistant, Mr. Gierad, here to help me. Okay. One second. Sensor board doesn't like to cooperate today. Let me give a further debug. Let's see. Let me put it on the ground. Okay. There seems to be a disconnection of the wire. Sorry, so there probably won't be a live demo today, but I will show you guys a demo later on. Thank you, Gierad. Let me talk about the implementation. The basic sensor unit consists of 3 parts. The first one is the 3 milliwatt laser diode. It's labeled as class 3A, which is eye safe for short period of direct exposure. And the second part is a pin photodiode, which converts the photon into a current. And the third part is the bandpass optic filter, which help us to improve SNR. We built a sensor board to measure signals from the sensor unit, so please find more details on this board in the paper. As I already mentioned, we constructed a steerable mirror platform. As you can see, there's an illustration on the left part, on the left of the screen that shows a complete sensor. Our board's firmware controls the motor and measures the reflected laser signal at 5 kHz. We used the FFT result as a features to train 2 label random forest classifier per object for vibration on and off detection. The result is fed into applications. Here is a video that shows a complete overview of the system. So as you can see, the user first tagged the objects of interest. Then our sensor scans across the whole room to find these tags based on the reflected light intensity. Here we'll show, here as you can see, the laser is being scanned across the room and the detected tag coordinates are shown on the laptop. So once these tags are found, our sensor cycles through them in a round-robin manner. So it collects 1 second data from each tag for vibration sensing. So I just turn on the coffee machine over there, and the detection result is shown on the screen. Here the microwave is running, and it's detected on the on the screen is shown. So right now, 3 things are happening: chopping, coffee machine, and microwave running, so all picked up by the sensor. Now, let me talk about the evaluation. We did the study at 4 locations, as shown here. So there was a kitchen, a gym, an office, and a workshop. We picked 6 objects in each location and attached 5 centimeters square virtual reflective tags to them. We then run an object usage detection study. So on the left, you can see the vibration spectrum of all tested objects when they are active. So to test the vibration interference, we collected the data at 4 conditions. First, when no object was active, then when 1 object was active, when 2 objects were active with all combinations, and finally, when all objects were active. So in each condition, we collected 3 seconds of data each time the laser landed on an object. We collected 10 rounds of data, which yields roughly 16,000 data points in total. We used leave 1 round out validation to avoid overfitting, and the result shows an object usage detection accuracy of 98.4%. Here, we break down the accuracies into the 4 data collection conditions. As one might expect, accuracy is the highest when you just turn on 1 object, but we can see that even when multiple appliances are active, Vibrosight still achieve high accuracies. We also tested our system 1 week later. This time, the data collected was only used for testing, so using the model we trained 1 week before. The result shows an accuracy of 96.2%, which was not significantly different, suggesting robustness over time. 3 seconds of sampling duration is a long time, especially there are many objects in a room that we are cycling between. And so we want to investigate shorter sampling durations. We found that we can use a duration of a half a second without sacrificing the accuracy. It would also be nice if Vibrosight could also automatically recognize objects without user labeling. So to see if vibration alone is distinctive enough to recognize these, we built a 24 label classifier with the data from all objects we collected from the study. Leave 1 round out validation shows an accuracy of 92.1%. I want to conclude my talk with some supplemental uses of Vibrosight. So first, human movement inevitably results in vibrations in the environment. Here we can see the signal from a user sitting down on the couch. Similarly, Vibrosight could monitor sleep restfulness if the tag is placed on a headboard or a bed frame. Vibrations resulting from knocking or typing on a tagged surface are also very apparent to Vibrosight. Thus, this is also possible to support some basic inputs, such as double knocking to create a notification. For devices with speakers, motors, or other actuators, it is possible to encode information in the form of vibrations. This opens a very interesting communication channel for richer applications. For example, devices could emit their brand, model name, model number, or IP address to expose additional functionalities. And finally, Vibrosight can detect small and movable objects by sensing the surface they are sitting on, such as a kitchen countertop or a work surface. Vibrations resulting from these small objects shakes the surface and thus can be detected by our system. Okay. Of course, Vibrosight also has several significant limitations. First of all, we require line of sight, which means that if the sensing beam is blocked by the user, we cannot detect vibration. And second limitation is the cycling speed. Since we have a round-robin looping mechanism, having more appliances in a room will lower the refresh rate. And finally, the mechanical steerable mirror might not be as durable as MEMS mirror, which is more compact and has a faster switching. We have open sourced this project, so you can find all the source materials in our GitHub, including the data we collected in the user study, source code for the software, firmware, 3D design files, and the PCB design files. And finally, I'm happy to take questions.
The live demo was also working right before the talk, and of course it broke. Any questions?
Hi, Daniel Ashbrook, University of Copenhagen. This is really fun work. I'm wondering if you have any thoughts on the trade-off between the amount of time it takes to sense each object and the number of objects you have in the room. So if I want to, really put a sensor on everything in the room, I might have 1,000 tags, and it could take a couple hours to scan the entire room.
Yes. So in the study, we found this quite interesting. So actually, as I mentioned, we investigated the sampling duration. We found for some objects that have intermittent and have like constant vibration patterns, for example, like microwave running, the dishwasher running, you can just pick up their vibration if the laser stay there for only 0.1 second, right? But for other appliances, for example, phone ringing, or I'm using a hammer, so these might require longer sampling. So actually, we can use adapt duration, sampling duration for to improve this refresh rate. Or another idea is if you have two lasers, right? So you can basically double the sampling. So actually in future work, we want to investigate what if we have, for example, the random dot projector. We have millions of random dots projected into the environment. In that case, the refresh rate won't be a problem because we're just sampling everything, monitor the entire room at the same time.
Okay, cool. So one other question is how do users actually indicate what these objects are? So again, if I have 1,000 objects, or even if I have 30 objects, how do I say this is the dishwasher, this is the coffee maker, and so on?
Yes. So the first solution for that is whenever user tag a surface, right? After our system detects where are the tags, we can turn on the visible light, point at a specific tag, ask the user what is that, and the user label that appliances. In that scenario. In another scenario, we can automatically recognize the vibration pattern of the objects at the first time they're used, based on the vibration signature.
Thanks.
Okay, let's thank the speaker.